Good morning, let's begin. This is Professor Grenfell's Math 12 Statistics class. We're continuing our lecture series in Chapter 9 on testing the differences between two parameters. So this is more hypothesis testing. We're going to look at example 9-7 on page 512, example 9-7, pertaining to cholesterol levels. And we'll read the problem for us. A dietitian wishes to see if a person's cholesterol level will change if the diet is supplemented by a certain mineral. 6 randomly selected subjects were pre-tested, and then they took the mineral supplement for a 6-week period. The results are shown in the table. The cholesterol level is measured in milligrams per deciliter. Okay, can it be concluded that the cholesterol level has been changed at alpha equals 0.10? Assume the variable is approximately normally distributed. So the first thing I want to make sure I do here is copy down all of the data carefully. So I have gone ahead and copied their table, and then I'm going to just go ahead and insert the values. So here I'm going to go column by column so that I don't accidentally mix up my test subjects. So this first subject had 210 as their beginning cholesterol level, and then after 6 weeks of the treatment, 190, and so on and so forth. And we'll fill in the rest of that carefully. Yes, so there is all of the data right there, all of the before and after. And here is one thing to notice. Anytime we have this sort of situation, before a treatment and after a treatment to determine the effectiveness of that treatment, we're going to want to track the individual subjects and their change over the course of the treatment. So for, if I'm participating in a subject, they need to keep my before figures along together with my after figures, or else they'll mess up the test. So that means that these samples are dependent. All right, the first data value is my before, and so automatically the second data value has to be, there's only one choice. It's my after readings. Okay. Now, normally what I would do is I would take all of the information from the problem, and so, I would record mu subscript d here. What else would we need to be, given here, or what else do we need to know? We need to know d bar and so on and so forth. And so I'm going to go ahead and make sure that I include all of that. And I want to make sure that I go ahead and have or get what to put in for all of these different values. And the only thing that we know so far is that alpha is 0.10. Okay, they've already given us the significance level with which to perform this hypothesis test. I take that back. We also know mu subscript d is going to be 0, because here we're trying to determine whether this mineral has any effect on cholesterol, and so our initial assumption always has to be, we can't assume that this is the miracle cure, right? What we have to do is we have to assume that this is no different than eating breakfast cereal. I mean, this does nothing, all right? So that there's going to be no difference between the before and after. And if evidence suggests otherwise, then, we will reject that as the null hypothesis. But most of the time, anytime we're testing to see if there is a difference between parameters, most of the time we make that initial assumption that the difference is exactly 0. All right, so since I want to get these missing values, the average for the differences and the standard deviation for the differences, then I need to go ahead and do that rough calculation by hand. So I'm not going to tell you every single step, but the first thing I'm going to do is I'm going to see what these differences are. And remember here we calculate d by doing x1 minus x2. That's the difference between the before and the after. Notice here we're looking at the negative change. Normally what we want to do is we want to say, okay, look, I started at this much and I increased to this much, or I decreased to this much. Normally what we do is we take the after amount and subtract away the before amount. If it's positive, then that's an increase. If it's negative, that's a decrease. Here, for whatever reason, the book is always starting us out looking at the before minus the after, and that is, I don't know, we just gotta be careful about that, because to me that's a little bit counterintuitive. I always look at the odometer after the trip and think about what it was before the trip, and I subtract before minus after. No. I subtract after minus before. But here we're doing it this way. So 210 minus 190, I'll go ahead and fill in all of these values here. So we're doing this, well, 2 reasons. We need to look at the sum of all of these differences and lift a little space for it there. And then the next thing that we're needing to consider is we need to look at the squares of all of these differences. So this is x1 minus x2 whole quantity squared, and we've already calculated x1 minus x2 for all of these, and so we're just going to go ahead and take that and square it. And we've got all of those values filled in carefully, and then we're also going to be looking at adding up all of those squares. All right, I noticed I made a little mistake there. That should have been a negative change, well, the subtraction should have been -1, and so this sum of all of the differences works out as 100. The sum of all of the differences squared, the squared differences, is 4,890. So both of those we need. We need the sum of the d's to calculate the average, so we'll use that here. And then we also need both of those figures, the sum of the d's and the sum of the d squareds, to calculate our standard deviation. And then both of those are used in the test statistic. So d bar is the sum of all of the d's divided by the total number of them. That's the mean of the differences, which works out as 16.7. And then here is our formula for the standard deviation. So it is a sample, and here we're talking about the differences distribution. So we have S subscript D is equal to, here, the square root of the whole entire quantity, n times the sum of the d squareds minus the sum of d, that whole quantity squared, all divided by n times n minus 1. And which, after a little bit of calculation, comes out as 25.4 milligrams per deciliter. Now, let's just go ahead and rewrite that here. And so here that is mu subscript d is equal to 0, d bar is equal to 16.7, s subscript d is 25.4, and then alpha equals 0.10. So they're just reorganizing that information. Now we're going to go through the steps for the hypothesis test. 1, stating the hypotheses, the null hypothesis, mu subscript d is equal to 0. The alternative hypothesis, mu subscript d is not equal to 0. So that is our claim. And notice we're going to be using a two-tailed test here. They just ask us, can it be concluded that the cholesterol changed, right? Notice if they asked, will it lower cholesterol, we would want to see a positive difference. We would, if for whatever reason we wanted to increase cholesterol, well then when we do before minus after, before would be lower and the after would be higher, so that would be a negative value. So that if that whole thing comes out as negative, then we'll notice that it increased cholesterol. So notice here there's no specific direction that they have in mind. They're not thinking, well, this will increase cholesterol. They're just kind of seeing, well, what will this do? Will it do 0 or will it do not 0? That's basically it. And step 2 is we will find the critical values and sketch the critical region. The book doesn't really make a big deal about sketching the critical region, but I feel like it's important, to just get a visual sense of what's going on. So here, it's not important in terms of looking up these values, because all we are doing here is we're saying, let's look in the column for a two-tailed test where alpha equals 0.10. And so notice that forces us to look in the second column. And then our degrees of freedom, I always include that when I'm making my sketch, is 5. So we'll look in row 5 and we find plus or minus 2.015 for our values. So we'll move on to step 3, compute the test statistic. Our equation for t is equal to d bar minus mu subscript d, all divided by s subscript d divided by the square root of n. So one thing to just point out here, make sure you are using parentheses if you're typing all of this into your calculator all at once. And that works out as a 1.610. And here is why I always make a sketch of what I'm looking at in step 2, so that after we do our work for step 3, we can come back and look at that and visually decide what we should do. For step 4, make the decision. So it's not in the rejection region, so don't reject the null hypothesis. Remember, that's all we do. We don't ever reject the alternative hypothesis. We just say, well, we can't reject the null hypothesis. We'll summarize 5. We'll say there's not enough evidence to suggest this mineral changes the cholesterol levels. And that's it. And at the risk of running a little bit long, I've decided, since example 9-8 is essentially just doing 9-7 again, we'll go ahead and include this in this video. So this is on the, just flip the page over. This is page 514. Okay. And in this exercise, it says to find the 90% confidence interval for the data in example 9-7. So you can see here we're going to use all of the same information. We don't have to redo all of those calculations, so that's why I wanted to include it in this video so we wouldn't have to redo it. So I always break it into two formulas. I say E is equal to T subscript alpha over 2. times S subscript D divided by the square root of n. And then the second piece of that, I just write it as mu subscript D is equal to D bar plus or minus E. So this is a kind of natural way to do it. You give a point estimate plus or minus the margin of error. And I feel like when we kind of chunk it into those two individual sort of pieces, it helps us to remember it a little bit easier. And here we're substituting in all of the same values. We would plug in 2.015 because we're looking in column 2 this time, because we're seeing that's the 90% confidence interval column. Still row 5, so it still gives us the same exact value, 2.015 times 25.4, all divided by the square root of 6. So that gives us 20.9. So this is going to be 16.7 plus or minus 20.9. So we'll do both of those. 16.7 minus 20.9 is negative 4.2. And then when we do 16.7 plus 20.9, that gives us 37.6. And so here we can actually express this in interval notation, or we can rewrite it like this. Mu subscript D is bounded between these two values. The interval is from negative 4.2 all the way to positive 37.6. All right, this is just two equivalent ways of expressing the same thing. You can put it like this in interval notation, or you can leave it like that, right? Notice the quiz will mark you wrong either way. There's no margin of error for that. But then I come back and give partial credit. Let's say some words about this example as it relates to the previous example, since it's the same data. Notice that 0 is contained inside this interval. We go from negative to positive, and so that means that 0 is one of the potential values for our mean. Now, in this case, since our mean is close enough, so all of these values inside this interval are all of the ones where we say, well, okay, our sample is close enough to this so that that is a potential value for the population parameter. And since this is close enough to 0, we'll say, okay, look, it just wiggled, but it didn't really move, okay? It moved slightly, you know, notice it looks like that, but if it's within the margin of error, we say, well, it's close enough to 0, so no significant change. And that will conclude 9-3.